All right, so last week we discussed the primordial transformation, and one of the motivation for starting primordial transformation is that when we discuss matching or maximum matching, we said that to have an upper bound for the size of the matching, we consider the minimum vertex cover problem. And similarly, when we discuss maximum independent set, we also establish an upper bound for the size of the independent set. That's the minimum edge cover. Okay, so we have two simple results. The first one is that the size of any matching is at most the size of any vertex cover. Okay, and obviously we are talking about the same graph. Okay, so fix a graph and consider any matching and any vertex cover, and you'll see the size of the matching is less than the size of the vertex cover. Okay. So similarly, when we discuss independent set, we have a similar relationship. I'll just write IS, okay, independent set. Okay. So now we know that given matching, we can apply the primordial transformation to get the vertex cover problem. So this is like the primal problem. And this is like the dual problem. Okay, so we've considered an example of maximum matching. We first modeled it as an integer program, and after that, we create the dual problem and figure out that this turns out to be the vertex cover problem. Okay. So similarly, the independent set problem, if we treat it as the primal problem, then the edge cover problem is the dual problem. Okay. So these two results basically says that the size or the solution of any primal problem is like it's at most the solution for the dual problem. Okay. So today we're going to show that this relationship is true for any primal dual problems. Okay. So the result is called weak duality, and formally this is so we're going to use the notation here. Okay, so let's quickly review the notation we have. Okay, so the primal problem we consider is a maximization problem. So the variables are x1, x2 up to xn. And this is the objective function. So this is the function that we try to maximize. Okay, so we want to find a proper setting of x1 up to xn so that this weighted sum of x is maximized. Okay, and also we have some constraints. And remember that all these constraints, they have the form of the left-hand side is a linear, also a weighted combination of the variable. And it is always a less than or equal to sign here. And the right-hand side is just a constant number. Okay, and we have in total m constraints, okay, and n variables. So this is like the standard form of the primal problem. And then we have the dual problem, okay? So in the dual problem, we always use y to denote the dual variable, okay? And we use, yeah, just y, okay? So you can see that these b coefficients, they are from the right-hand side of the constraints, okay? So b1, b2, b3, they are the right-hand side of the constraints in the primal problem, but in the dual problem, it becomes the coefficient in the objective function, okay? And for the dual problem, the right-hand side of the constraints are from the coefficient in the primal problem, okay? Okay, so with that, so I'm going to denote x. So this is a feasible solution for the primal problem. And y is a feasible solution for the dual problem. Okay, so this feasible means the solution satisfies all the constraints, okay? So for example, if I say that x, some solution x is a feasible solution, then this means is solution x. It satisfies the first constraint, the second constraint, the third, and so on. It satisfies all the constraints. So in that case, we say that it's a feasible solution, okay? So this is feasible. It means x satisfies all m constraints. Okay. Now, y also satisfies all the constraints in the dual problem, okay? But there's a small difference that in the dual problem, we do not have m constraints. We have n constraints. Why do we have n constraints? The reason is that we use these constraints to make sure that the combination of the coefficient, combination of these constraints is an upper bound for the objective function. So we have to make sure that when we combine these constraints, the coefficient of x1 is at least c1. Okay, so the physical meaning, recall that the left-hand side is basically the coefficient of x1, and this is the coefficient of x2, x3. So we have to make sure that this coefficient is at least their original coefficient, so that we get that upper bound. Okay, so that's why we have n constraints. All right, so the weak duality basically says this. So this is like, this is the objective value. Okay, so the left-hand side is the objective value of the solution x. So x is a solution for the primal problem, okay? And the right-hand side is the objective value of y, which is a feasible solution for the dual problem. Okay. So this is the main result that we're going to prove today, okay? So these previous two inequalities, they are like the special cases for this one, okay? Because when you consider the size of any matching, this is like the objective value for this objective function, okay? So first, you have to make sure that the edges that you pick is a feasible solution, meaning they cannot share endpoints, okay? And then you consider the corresponding objective value, okay? So the objective value here is just the number of edges that you pick, okay? And we already showed that the number of edges you pick in a matching is at most the number of vertices that you pick to cover all the edges. That is the size of the vertex cover, okay? So this is the objective function for the vertex cover problem. The physical meaning here is the number of vertices that you choose, okay? Okay. So this inequality basically says that whenever you have a primal problem and you get a dual problem, you always have this upper bound, okay? So as long as you have a feasible solution for the primal problem, you can always get an upper bound by finding a feasible solution for the dual problem. And the objective value for the dual solution is an upper bound, okay? 所以这边最重要的事情就是每一次你手上有一个问题，任何一个问题都可以，只要这种问题是 optimization 的问题，你有一些 objective function， 你有一些限制，然后你可能手上已经有一个 solution 了，那你想要做的事情是你要找到这个 solution 的 upper bound， 譬如说你想要说服别人说你手上这个 solution 已经是最好，所以你要找到一个 match 的 upper bound。那这个他就告诉你一个找到 upper bound 的方法，那就第一步骤就是要找到 dual problem。然后第二个步骤就是要找到dual problem 的 feasible solution，OK， 所以这个 dual problem 的 feasible solution， 任何一个 feasible solution 都可以带进去，它的 objective value 就会是本来的 upper bound，OK。对，然后我这里的 CTX 就是我之前应该有说，就是这个 CTX 就是C 这个 vector 跟 X 这个 vector 有点像是乘在一起 ，OK。因为我们这边的所有的CBXY 都是 column 的 vector。Okay, 所以如果你要把它们乘在一起，你就要 transpose 才可以乘在一起。OK， 到这边有问题吗？我还没有真正，我们接下来要说这个很快，但是我只是想确保一下，目前这有点像是前情提要，有没有不清楚的地方？OK， 好。Okay, so next we're going to prove the weak duality, okay? So CTX, so expanding this, we get C1x1 plus C2x2 Okay, so this is where we start, and the goal is to show that this is a most okay. So observe that we have n variables in a primal problem. So we have x1 up to xn, but in a dual problem, we have m variables, ym up to ym. And the reason is that we have a dual variable for every constraint. And we said that we have m constraints in the primal problem. Therefore, we have m dual variables. Okay. So this is our goal, okay? Okay. So we're going to use the inequalities in this slide to complete the proof, okay? So first of all, I need to replace C1 with something related to B and A and Y, okay? So clearly, the only inequality we can use is like this sets of constraints. So this set of constraints says we have an upper bound for C1, okay? So this sum is greater than or equal to C1, okay? So see if I can, yeah, okay. Okay? So this sum is greater than or equal to C1, okay? So next, we have to find the upper bound for C2. Okay? So this is greater than or equal to C2. Okay. So basically, I just copy-paste the previous constraints into this slide. So the last Cn okay? Okay, now we've removed C1, okay, and basically all the coefficients C, okay? Next, we have to put every term that is related to y1 together. So here we can see that we have this. So basically we have n terms related to y1. We're going to combine these terms, okay? So combining all terms related to y1, we get a11x1 plus a12x2 okay? Next, terms related to y2. So we get a21x1 plus a22x2 up to a2nxn. Okay. Okay, so the last terms related to ym. So we get am1x1 plus am2x2 up to amnxn. Okay. So this is an equal sign. So what we did is just rearrange the terms here, and we collect all the terms related to y1 together, collecting all the terms related to y2 together. Okay. And the reason is that in our Go, we have like a weighted combination of y1, y2, up to ym, okay? Now to finish the proof, all we have to do is to hope that this sum is at most B1, and this sum is at most B2. And so up to, so am1 x1 plus blah, blah, blah is at most Bm. Then the proof is done, okay? So we'll compare these two numbers. Okay. And basically, this is the first constraint in the primal problem. Okay, so a11 x1 plus a12 x2 is MOS B1. Okay. Okay. So the same right hand side, the same left hand side. Okay. And the second term, I can copy this to here. Okay, so now you can compare. Okay. So this time we're going to consider the second constraint in the primal problem. So a21 x1, a22 x2, up to a2n xn. Okay, and this is MOS B2. Okay. So this blue sum is MOS B2. Okay. So the last sum is the same. Okay. So according to the constraint, the last constraint in the primal problem, the sum is MOS Bn. Okay. So we get our result. So that's why whenever you have a primal problem and you get a feasible solution for the primal problem, and then you get a dual problem, a dual solution y, okay, then you can use that y to create the upper bound. Okay. Okay, so I still have 5 minutes. So I'm going to use 5 minutes to discuss this maximum weighted matching problem and give you the integer program formulation. Okay. So let me first explain the problem input and output. Okay. And in your homework, you're going to transform this problem that we're going to define into the dual problem. Okay. All right. So again, we have a bipolar graph, and the goal is to pick a matching, but this time we want to have a matching that has the maximum total weight, okay? So we don't count the number of edges that you choose. We only count, or we compute the sum of the weights of the chosen edges, okay? So for example, if you choose these two edges, well, this is a feasible solution because edges that you choose do not share endpoints. And the objective value is 4 plus 2, so it's 6, okay? Now you can also consider another solution. So because obviously this is not the best, so the best matching is a total weight of 9. Okay. All right, so basically this is like a general version of the maximum matching problem, okay? So we extend the original problem and we add weights to the edges and want to maximize the total weight. So by the way, I'm going to upload the second assignment tonight to Moodle, okay? So once again, you have 1 week to complete the assignment. And I think we don't have time to discuss the solutions next week. If so, I'm going to upload a video explaining the solution, okay? Yeah, okay. All right, so let me give you the integer program of this maximum weighted matching problem. So whenever you want to create an integer program, the first step is always to define the variables, okay? And because this is a maximum weighted matching problem, the goal is to pick edges. So naturally, we will create a variable for every edge. Okay, so here we have, so perhaps I should use V1, V2, U1. Okay. So because I'm going to use X to denote the variable instead of the vertices. Okay. So let's change the vertices to V1 up to V4. Now Xi Xi is a binary variable indicating whether EI is chosen or not, okay? So these are our variables. So in this particular instance, we have 4 variables corresponding to E1, E2, E3, and E4, okay? So I think the only difference between this integer program and the one that we discussed last week is the objective function, okay? So because in the maximum matching problem, the objective is to maximize the number of chosen edges, okay? But this time, we do not simply count the number of edges, we count the weights, okay? So this will be our objective function, okay? So this time, the coefficient of every variable is the corresponding edge weight. And the rationale is simple because if you choose E1, that is if Xi is 1, then it should contribute a weight of 6. So I just write 6 times x1. So if you set x1 to 1, you get a 6. If you set x1 to 0, you get 0. Okay? So similar idea applies to the remaining edges. Okay? Right, so really this is the only difference because all the constraints are the same. So the constraints is to make sure that for every vertex, we can choose at most one of its instant edges. So for example, for V1, we can choose at most one edge from E1 and E3. So we can write x1 plus x3 is at most 1, okay? So the effect of this inequality is that I can set at most 1 of x1 or x3 to 1, okay? So you cannot set both x1, x3 to 1, no, okay? And for V2, it's x2 plus x4 at most 1 because edges instant to V2 are E2 and E4. Therefore, we have x2 plus x4 is at most 1, okay? And for V3, and for V4, okay? So this is the dual problem, okay? Oh, sorry, the primal problem. Okay, then you can transform this problem into the dual problem, okay? So whenever you try to transform the primal problem into a dual problem, you only need to focus on the objective function and this constraint. So if you have this like binary variable constraints, you don't have to consider those constraints in the dual transformation. So in the dual transformation, you just consider these standard constraints. Okay, so first of all, it's an inequality, and the right-hand side. So the right-hand side is some constant, and the left-hand side is some combination of some weighted combination of the variable. Okay, and it is a less than or equal to sign. Okay， 所以这边的重点就是在去建这个 dual problem 的时候，你只要去管 objective function， 然后去管这些一般的限制式，就是这些变数的 weighted combination， 然后这个限制式一定都是小于等于，然后右边一定都是一个 constant， 对一个跟变数无关的 scalar 就是数字就对了。OK， 那像这种，这个你在做 dual 的 transformation 的时候就可以先忽略不管。OK， 好，所以就差不多是这样。我刚好说今天晚上我会上传第2次的作业 ，OK， 然后大家一样有1个礼拜可以写。如果下礼拜没办法检讨的话，我就会上传影片到 YouTube。OK， 好，那我们今天就上到这里。